we have studied Lyapunov theory, and we learned that there are certain limitations of this Lyapunov theory. Main limitation is due to the fact that it only provides sufficient conditions. That is, for example, if you take a positive definite function for a system, and its derivative along system trajectories comes out to be negative semi-definite, then what is your conclusion? You conclude that the equilibrium point is stable. But what about asymptotic stability? You cannot say anything about asymptotic stability. So in today's lecture, we are going to talk about invariance set theorems. What is the benefit of these theorems? With the help of these theorems, we can basically augment these theorems with Lyapunov theory to conclude the asymptotic stability of equilibrium point for a system. That is for the case when the derivative of candidate Lyapunov function comes out to be negative semi-definite, then you can augment that information with the invariance set theorems to conclude the asymptotic stability. So before we give mathematical description of these theorems, let's elaborate the concept with a simple example. And we take our favorite example of the pendulum system described by these state equations. And we remember that we had taken this candidate Lyapunov function for this system and computed its derivative along system trajectories, and this derivative came out to be negative semi-definite, and hence we concluded that equilibrium point was stable. So is it also asymptotically stable? With this theory, we cannot say anything. However, we have some intuitive knowledge about this process as well. We know that this V dot will be equal to 0 when x2 is equal to 0. V dot will be equal to 0 only when x2 is equal to 0. x1 can be anything, but x2 has to be 0 for V dot to be equal to 0. If x2 is not equal to 0, then it will be strictly negative. So V dot is equal to 0, trajectories must be confined to this line. What is x2? x1 is the angular position and x2 is the angular velocity. And you see that this angular velocity can be identically equal to 0 only when the position is also equal to 0. x2 is also equal to 0 when this pendulum is at its maximum angular position, but that is only for some instantaneous time. This x2 can be identically equal to 0 only when x1 is also equal to 0. It means that we can use our intuitive knowledge to conclude about the asymptotic stability of the equilibrium point. With Lyapunov theory, what we conclude is that the equilibrium point is stable, but we cannot say anything about asymptotic stability. However, we can augment our intuitive knowledge and hence conclude the asymptotic stability. For this particular process, for this particular system, we had the physical understanding of the process as well. But even if we do not have the physical understanding, the same will be conclusion from the mathematical model as well, as we can see it over here. That is, when x2 is equal to 0, identically equal to 0, it means that its derivative will also be equal to 0. If x2 is identically equal to 0, then its derivative is also equal to 0. x2 dot equal to 0 from this equation, x2 is equal to 0, x2 dot equal to 0 means sine of x1 is also equal to 0, and which means that x1 is equal to 0. So x2 can be identically equal to 0 only when x1 is also equal to 0. That means this system will be the equilibrium point of this system at origin will be asymptotically stable. So what is conclusion? We had some information from Lyapunov theory, and then we had some information from the mathematical model or from the physical understanding of the process, and we augmented the two informations to tell about the asymptotic stability of the equilibrium point. This is basic concept of the invariance set theorems, and that is also summarized in this statement. If the candidate Lyapunov function, its derivative comes out to be negative semi-definite, and if we can establish that no trajectory can stay identically at points where v dot is equal to 0 except at origin, then origin is asymptotically stable. As we have illustrated in previous case, v dot equal to 0 was only possible when x2 was equal to 0, and x2 is only 0 when x1 is 0. So if that is the case, then origin is asymptotically stable. This theorem is quite intuitive, and this statement is quite intuitive. Any confusion up to this point? In previous example, was that possible to have x2 equal to 0 and x1 equal to non-zero constant? ये क्या possible था कि ये हो सके? इंस्टेंटेनियसली तो हो सकता है, आइडेंटिकली नहीं हो सकता. आइडेंटिकली नहीं हो सकता कि वेलोसिटी 0 हो और पोजीशन नॉन ज़ीरो हो. This velocity can be equal to 0 when this ball pendulum is at extreme positions. That is possible for some instantaneous time only, not identically, right? There is another possibility. This pendulum oscillates about its equilibrium point and then finally settles down over here. Here velocity is equal to 0. What about position? Position is also equal to 0. So velocity can be identically equal to 0 only when angular position is also equal to 0. So here is the summary of that discussion and theorem which we are going to study, that describes this information in more mathematical way and more generic way. And to study that theorem, we have another concept which we need to understand: invariant set. What is an invariant set? A set G is invariant set for a dynamic system if every system trajectory which starts from a point in G remains in G for all future time. A set will be invariant set if trajectory starting from within this set will stay in this set, then that set will be invariant set. Can you give some examples of invariant set? Here is one example, and you may give some other examples as well. Equilibrium point. If trajectories start equilibrium point, this is a set. So if trajectories start from this set, trajectories will stay in that set. That means that this equilibrium point is an invariant set. Any other example of invariant set? Right. So domain of attraction of an equilibrium point is also an invariant set. If trajectories start from this set, then trajectories will stay in this set. So this is another example of invariant set. Any other example? Whole state space, that is trivial case. Trajectories trajectories will of course start from the state space and it will stay in that state space. Any trajectory in state space, that is also invariant set. If you have some trajectory, so you start from this trajectory, you will stay on that trajectory. Limit cycle. Limit cycle is also basically some trajectory, so a special case of a trajectory, and that limit cycle is also an invariant set. If trajectories start from any point in this limit cycle, then that trajectory stays on that limit cycle within in that set. So that is an invariant set. So this concept is clear. Invariant set, this concept is clear. So here is a theorem presented by this, I think this name is French name, LaSalle's invariance theorem. What is the statement of this theorem? We consider a nonlinear system where f of x is some continuous function, and for this system we take a function v of x with continuous partial derivatives, and furthermore we have some assumptions, and firstly omega L, L is some positive constant, and omega L is a set of points in state space. Omega L is set of points in state space for which this condition is satisfied, and this set is bounded. Furthermore, the derivative of this function is less than or equal to 0 for all x in this set. In addition to that, let R be set of all points within omega L where v dot is equal to 0. We know that v dot is either less than or equal to 0. For certain points in state space this will be less than 0, and for certain points it will be equal to 0. So set of points for which this v dot is equal to 0, that set is denoted by R. And M is the largest invariant set in R. Then every solution x of t originating in omega L tends to M as t tends to infinity. This statement is still a little bit difficult to understand, so let's explain it with the help of a diagram. Again we take a simple case, that is system with two states, and here is the state space. Now x1 on this axis and x2 on this axis. We are talking about system with two states, that is easy to visualize. This v is some function of x, so on this third axis we have taken v, right? This v is some function of x1 and x2. Function of x1 x2 means that corresponding to each point we have some value of v. This set inside this circle, in this side circle, this set is omega L. All the points inside this circle, this set is omega L. For all the points inside this circle, v will be less than L. Is that clear? So this circle, in all the points inside this circle, that set is omega L. We know that v dot, we have not shown v dot in this diagram. We have shown only v. V dot is the time derivative of v. That is not shown over here, and we know that it can be either less than or equal to 0. For certain points it will be less than 0, for other points it will be exactly equal to 0. So the set of points for which this v dot is equal to 0, that will be a subset of this bigger set, right? So that set is denoted with R. Clear? And there is another set inside R which is invariant set. So if that is the case, then any trajectory starting from this set will finally converge to the invariant set. This is the statement of this theorem, right? Is it clear or not? So this theorem states that any trajectory starting from this set omega L will finally reach to this invariant set. And what will be the case if invariant set consists of a single point, that is the origin? This theorem states that the trajectories will converge to the invariant set, and if invariant set is the only point, origin, so then the equilibrium point will be asymptotically stable. So this is a corollary of this theorem. If M consists of origin, then the equilibrium point is asymptotically stable. It is a little bit difficult concept, but anyway, we can further elaborate it with the help of a few more examples.